Alright, welcome back everybody, and today we're going to be using some complex analysis to evaluate this improper integral right here from minus infinity to infinity of cosine of x over this pi squared minus 4x squared right here. So this is a bit of a weird function to integrate, but it turns out that this integral works out quite nicely in the end. So let's take a look at this function first of all, actually, because it's quite interesting. You might notice that usually if we have a cosine, we would have some kind of positive function at the bottom right here in the denominator, but here we have pi squared minus 4x squared, and the graph of that actually looks like this. It's an upside down u, and well, that means you're going to introduce these zeros right here, and since we're on the denominator, that means we're going to have singularities at these points. But the thing is, the nice thing about this denominator is that it actually intersects the x-axis at minus pi on 2 and pi on 2, and that's exactly the intercepts of this cosine function. So our cosine looks something like this. It also intercepts at minus pi on 2 to pi on 2, and in fact if you take the limit of this thing right here as x approaches plus or minus pi on 2, you actually get some kind of result out of this. So the graph of this looks nice and continuous. I think it's like something like this. If you graph it out and there's loss, it's some weird decaying cos graph. That's an ugly graph, but I hope you guys get the idea. So this thing is actually defined everywhere on the real axis, which is quite nice, so we can integrate this thing. So let's now jump to solving this integral using complex analysis. So as always, we want to define for ourselves a new complex valued function. Let's call it f of z, and we're just going to be letting it equal to this integrand right here, but with some modifications. So first of all, we're going to be replacing all the x's with z, so we're switching from real valued inputs to complex valued inputs. First of all, let's take a look at this denominator. We have pi squared, and then minus 4, and now instead of x squared, we're going to have z squared. But now instead of taking cosine right here, because in the complex plane, cosine is defined to be the difference of two exponential functions. Usually when we have sine or cosine in our integrand, we replace it with e to the iz. And the reason for that is if you take the real part of e to the iz, or actually if we take the real part of a function f of z, we actually get back to this integrand right here, which is quite nice. And the nice thing is with this function right here, it's only one exponential term to deal with, so it's just easier to do a couple of the calculations with. So with that out of the way, we've gotten our function. Let's figure out what the poles are. Well, we know where the poles are. It's exactly plus or minus pi on 2. You can first note that this is kind of like a difference of two squares. We're going to have pi plus 2x and pi minus 2x, and if you set that equal to 0, you can solve for where the denominator equals to 0, and it turns out it's plus or minus pi on 2. So that means that our z, the poles, are where z is equal to plus or minus pi on 2, so we actually have poles on the real axis. So now we have our poles figured out. Let's figure out what contour we should use. So if we take a look at the complex plane like so, we're just going to take a look at the upper half for now. Where are our poles? Well, I'll mark it in red right here. Our poles are at minus pi on 2 as well as pi on 2. And ideally, we don't want to integrate over these poles right here, even though we're going from minus infinity to infinity. So usually with these integrals right here, what we do is we start off at some point minus r, and we try to get to r right here. And later we're going to be taking the limit as our r approaches infinity, so that when we integrate across this line right here, we actually get this integral back. So first of all, let's figure out how we can get from minus r to r. We're going to travel along the real axis right here, but we don't want to cross over the singularity, so what we're going to do instead is we're going to make a little bit of a jump. We're going to go for a little bit of a detour around this pole, and once we get to the other side, we can keep going, but we run into another pole, which is not good. So let's do the same thing. Let's jump over this a little bit. So we're going to have another little semicircle like so. And now we can keep going on to r. And we actually want to make a contour, so we can use Cauchy's integral theorem. I think that's what it's called. So in order to close off the loop, let's go along a big semicircular arc like so. Alright, so this is a pretty interesting looking contour. Let's give each of these paths a couple names. I'm going to first of all call the path that goes along up here big gamma, and I'm going to call each of these little paths right here little gamma 1, then we have little gamma 2, little gamma 3, little gamma 4, as well as little gamma 5 like so. So we have a lot of paths to integrate over. And I'm going to call the whole entire contour C like so. And notice one cool thing right here, this contour doesn't enclose any poles. Usually if we have poles inside of our contour, we would use Cauchy's residue theorem. For example, if you decide to, instead of taking the path above, if you decide to take the path below, you would use Cauchy's residue theorem because you would be enclosing those poles in that case. But here I decided to go above so that we don't need to use Cauchy's residue theorem. So that means it's just less work to do. Alright, so we have our contour figured out. Notice that we're going from minus r to r, which means the radius of this big circle is exactly r. And r is a really big number. We're going to be taking the limit as our r approaches infinity soon. And how about with these little semicircles right here? How can we define that a little bit better? Well, we're going to define its radius to be epsilon. So each of these little radii right here are going to be some distance of epsilon. And we're going to be taking a limit as our epsilon approaches 0 as well. And you can imagine like these little circles right here kind of squeezing in onto each of these singularities right here, and this whole entire contour kind of expanding out. Alright, so we've gotten our contour figured out. Let's write down a couple of integrals. Let's get rid of this limit right here. I want to do some stuff right here. First of all, we're going to calculate the contour integral over C. And notice the contour integral over C, that's just composed of multiple separate paths right here. So notice that can be decomposed into the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3 plus the integral over gamma 4 plus the integral over gamma 5. That's a lot of integrals to calculate, plus the integral over big gamma like so. It's plus the integral over big gamma. Okay, and what can we say so far about this? Well, notice that this contour integral will actually become 0. So this integral will be 0, and why is that? Well, since we're going on a nice closed contour that doesn't enclose any poles, and everywhere inside of this domain except for these two poles is analytic. So by Cauchy's integral theorem, it says that any integral over a closed loop of a function in an analytic domain is exactly 0. So we've figured out our first integral right here, and now we have to calculate all of these integrals right here. Luckily, they're not too hard to calculate except for like 2 of them, 2 or 3 of them. But yeah, let's just get straight into it. So first of all, let's figure out what gamma 1 is equal to. Integral over gamma 1 of f of z dz, what exactly is that? This is really quite easy to do because notice that's just on the real path from minus r to this point right here. And that point is actually minus pi on 2. And then since we're going back a little bit, we're going to subtract off an epsilon. So this is the exact same thing as the integral from minus r to minus pi on 2. And then we're going to subtract off a little bit of an epsilon right here. And then we have our f of z. But notice this is on the real axis, so we don't really need to use these. We can just use f of x. But f of x is exactly this thing right here. So we have e to the I x over pi squared minus 4x squared dx like so. Okay, that's nice, but what's not nice is these bounds right here. They have all these minuses in them, which we would like to kind of get rid of somehow. So how can we do that? Well, we can just introduce a simple substitution. For example, let the t be equal to minus x, which means that dt is equal to minus dx. And if we apply the substitution right here, what we get is the integral. If we plug minus r into this minus x right here, then t will be r. And then same thing up here, we're just going to get rid of all these negatives. So we're going to have pi on 2 plus epsilon. And then we have e to the, well, x will become minus t. So we have e to the minus it over pi squared. And notice x squared is an even function, which means if you plug minus something into it, it's still the something itself. So we still have minus 4 t squared like so. You can pause the video and confirm that for yourself. And then dx, well, that's minus dt. So we're going to have minus dt hanging off the ends like so. Alright, so next notice that these bounds are kind of misoriented. So let's reorient it properly by using this negative. So we're going to put this negative inside of this integral, and then we're going to have the integral from pi on 2 plus epsilon all the way up to r of e to the minus I. And notice t is just a dummy variable, so let's just change it back to x, so e to the minus ix over pi squared minus 4x squared dx like so. Alright, so I'm just going to leave it at that now for the first integral. We've done quite a bit of work on this already, and we actually need another integral in order to do more work on this. So let's just leave it for now. So we've just figured out that our first integral is nicely equal to the integral from pi on 2 plus epsilon all the way up to r of e to the minus ix over pi squared minus 4x squared dx. Okay, and now I'm going to make a bit of a jump, and we're going to take a visit to the integral over gamma 5. So now we're going to take a look at the integral over gamma 5 of f of z dz. Same deal as before. We're on the real axis, so we can just change that to x's. So this is the integral, well, gamma 5 is from pi on 2 plus epsilon. So pi on 2 plus epsilon, and we're going all the way up to r, and f of x is exactly e to the ix over pi squared minus 4x squared dx. Okay, notice one cool thing right here. The bounds of this integral of gamma 5 is the exact same thing as the bounds we currently have of gamma 1. And notice gamma 1 and gamma 5 will eventually be added up together. So let's actually just add them up right now. We know this is the expression for gamma 5, so what would happen if we just add on the integral over gamma 1? Well, what we would get is the integral. Notice that these bounds of the integral are the exact same, which means all we need to do is add the integrands together. So we have the integral from pi on 2 plus epsilon all the way up to r of e to the ix plus e to the minus ix. And notice common denominator, so let's just divide it through by pi squared minus 4x squared dx, like so. Okay, and why exactly did I do that? Notice the numerator right here. That looks an awful lot like the complex definition of the cosine right here. We have e to the I something plus e to the minus I something, and all we're really missing is a division by 2. So let's just, well, force a division by 2. So let's introduce a factor of 2 down here. And we can't just multiply by 2 on the denominator. We have to do the same for the top as well. So you have a 2 in front there. So this, remember, that's the integral over gamma 1 plus the integral over gamma 5. And well, by doing this, we have this part right here, which is exactly cosine of x, which is basically what we have right here, which is really quite nice. So what does that mean? It means that if we have gamma 1, integral over gamma 1 plus the integral over gamma 5, this is going to give us 2 times. We have the integral over pi on 2 plus epsilon all the way up to r of cosine of x, all divided by pi squared minus 4x squared, like so. Okay, so this is really nice because now we've evaluated the integral over gamma 1 as well as the integral over gamma 5 kind of together. So we can get rid of this now because we just found that if you have gamma 1 plus gamma 5, you're going to get 2 times the integral from pi on 2 plus epsilon all the way up to r of cosine of x, all divided by pi squared minus 4x squared, which is quite nice. So we've figured out 2 integrals right now. Let's go on to the third integral. And the third integral I want to take a look at is the integral over gamma 3 right here. So gamma 3 is this middle segment kind of in the middle right there. So we have the integral over gamma 3 right now of f of z dz. What is that equal to? Well, again, we're on the real axis, so that's the integral. We're going from minus pi on 2 plus epsilon, so this is minus pi on 2. We're starting right here, which is what we have to add epsilon to get there, so we have minus pi on 2 plus epsilon. And where are we going to? We're going to this point right here, but that's pi on 2 minus epsilon, so we have pi on 2 minus epsilon right here of f of z dt, but on the real axis, so we're just going to take f of x, and that's exactly e to the ix over pi squared minus 4x squared dx, like so. And now we're going to take advantage of a little bit of symmetry, because notice if you, for example, factor a negative out of this lower bounds right here, if you just factor out negative, we're going to have pi on 2 minus epsilon, but hey, that's the exact same thing up here. And what I'm going to do further is I'm going to split this integral up into 2 intervals. So now this integral is the same thing as the integral from minus pi on 2 minus epsilon to 0 of e to the ix over pi squared minus 4x squared dx plus the integral from 0 to pi over 2 minus epsilon of e to the ix over pi squared minus 4x squared dx. And hopefully you can kind of see where I'm going with this. I'm basically doing what we did to gamma 1 and gamma 5, except this time I'm decomposing gamma 3 into two separate integrals and kind of mushing them back together somehow. So we want to kind of add these two integrals again, so we want to get the same bounds. Nicely, this bound is the exact negative of this bound right here. So we're just going to do a simple substitution. I'll do it over here, I guess. So if we let, for example, t be equal to minus x again, so dt is equal to minus dx. What does that mean? It means that all this stuff now is equal to the integral. And notice we're just applying this to this integral right here because this bound right here has the negative which we want to kind of fix. We're not doing it to this integral, only this one. So if we apply the substitution to this integral right here, what are we going to get? We're going to get, well, first of all, this is going to turn into just its positive version. So we're just going to have pi on 2 minus epsilon, and we're going to go all the way up to 0. And then e to the minus it, just like before, because x turns into minus t, and then pi squared. Notice x squared again is an even function, so we have minus 4t squared like so, and then minus dt, because that's exactly dx. Okay, now we can add this with the integral from 0 to pi on 2 minus epsilon of e to the ix over pi squared minus 4x squared dx. And well, notice we can distribute this negative into this integral right here. So in doing so, we're going to flip the bounds right here. So these bounds are going to switch around, and we're going to have the same bounds on both these integrals, which means we can add them together. So now we have the integral from 0 to pi on 2 minus epsilon. We're going to add these two integrands together right here, and notice they have the same denominator, which means that we really only need to add the numerator. So we have e to the ix. T is just a dummy variable. Let's just switch it back to x. It really doesn't matter. So we have plus e to the I minus ix, all divided by pi squared minus 4x squared dx, like so. Okay, and just like before, we can form some kind of cosine up here by multiplying the denominator by 2 and multiplying the numerator by 2, or just the whole entire thing by 2. Okay, and let's rub this stuff out. We need a bit more space. This part right here, right there, that's our cosine. So now we have that integral over gamma 3 is nothing but 2 times the integral from 0 to pi on 2 minus epsilon of cosine of x, all divided by pi squared minus 4x squared dx. Okay, so that's our third integral figured out. This is exactly the integral over gamma 3. So let's put that back into our working. So we just figured out that the integral over gamma 3 contributes, I forgot a dx right here, contributes this extra term of 2 times the integral from 0 to pi on 2 minus epsilon of cosine of x, all divided by pi squared minus 4x squared dx. Okay, so that's the integral over gamma 3 figured out, and now let's move on to the integral over gamma 2. We're going to figure out this one next now. So now the integral over gamma 2 of f of z dz. Here we can't change our z to x because, well, we're in the complex plane right here, we're outside the real axis. But let's just write things down a little bit. This is the integral over gamma 2 of f of z, which is exactly this thing right here. So we have e to the I z over pi squared minus 4z squared dz. Okay, and what exactly is gamma 2? Gamma 2 is this semicircle thing right here, and what I want to do is parametrize that path. So in order to parametrize this thing, I guess the best way to do it is do a simple substitution. So if we let z be equal to the parametrization, well, how can we parametrize this path right here? Well, we're doing a little bit of a semicircle around minus pi on 2, so we kind of have to start at minus pi on 2, and we're doing a little bit of a circle thing here. So all we have to do is add epsilon e to the I theta, because e to the I theta will give us the set of points that form a circle around minus pi and 2, and the radius is exactly epsilon. So we're doing epsilon e to the I theta. That's going to give us a circle of radius epsilon centered around minus pi and 2. And now let's differentiate both sides. So dz is equal to, differentiating distance isn't too bad, just some basic chain rule. So I times epsilon e to the I theta d theta, like so. And now we can substitute all of this stuff back in. Actually, I forgot one thing right here. We have to figure out the domain for theta, because theta, we want to go from this left side right here to the right side, which means theta starts from pi and it goes all the way to 0. So I'm going to use a bit of weird notation right here. We're going to go from pi to 0, like so. Okay, so now we can substitute everything back in. This is the integral from pi to 0 of e to the I. And now what exactly is our z? Our z is this weird thing right here. So we have minus pi and 2 plus epsilon e to the I theta, like so. And all this is divided through by pi squared minus 4. And z squared, well, we're just going to take this thing right here but square it. So minus pi on 2 plus epsilon e to the I theta squared, like so. And our dz, well, our dz is exactly this weird thing right here again. So we have I times epsilon e to the I theta d theta, like so. Okay, and remember what I said before. We wanted to take the limit as our epsilon approaches 0 and our r approaches infinity. Well, there's no r's inside of this integral, so the only thing we can take the limit of is our epsilon. And it's kind of important that we do it now, otherwise things will get incredibly messy. So if we take the limit as our epsilon approaches 0 right here. So if we interchange these limits right here, we're going to take the limit as our epsilon approaches 0 on this integrand right here. So in the limit as our epsilon approaches 0, what will this integral turn into? It's going to turn into the integral from pi to 0 of, well, as epsilon gets smaller and smaller and smaller right here, this term right here, that's going to vanish off to 0, leaving us with e to the I times minus pi and 2. But notice that's exactly minus I, because if you start at 1 and swing down an angle of minus pi and 2, you're going to land on minus I. And notice we have an I right here. So minus I times I, well, I times I is negative 1, and negative of a negative 1, that's exactly 1. So in fact, this whole thing right here will cancel out with this I. It's just going to be 1. And all really left with is e to the I theta. And then we have epsilon, all divided through by pi squared minus 4, minus pi on 2, plus epsilon e to the I theta d theta, like so. And let's just focus on this part right here. Notice what will happen when our theta turns into 0. Well, we're going to have 0 here first of all, but more importantly, when this epsilon here becomes 0, I forgot a squared here. When this epsilon becomes 0, we're just going to be left with minus pi and 2 squared. But minus pi and 2 squared, that's pi squared over 4. Multiply that by 4, I'm going to get rid of this 4 down here. So overall, this whole term right here is pi squared, but you have pi squared minus pi squared. So that's a 0. So in fact, if you let epsilon be equal to 0, you end up with a 0 over 0 situation. And that just means we have to use L'Hopital. So let's differentiate the top with respect to epsilon, so dd epsilon, and differentiate the bottom with respect to epsilon, so dd epsilon down there. And what are we left with? We're left with the integral from pi to 0 of e to the I theta. And now derivative of epsilon with respect to epsilon up here, that's exactly 1. And then we're going to divide that through by, now derivative of the bottom right here, derivative of pi squared is exactly 0. And then we have this thing left right here. And in order to differentiate this thing, it's best just to use some chain rule. So first of all, outside derivative, we have the squared right here. Make it jump down. That's going to become a negative 8 down there. Then we still have the same junk inside, so minus pi squared over 2. So minus pi over 2 plus epsilon e to the I theta. And now we have to take the derivative of the inside right here. Notice epsilon is kind of like our variable. So we have this constant multiple of epsilon I theta. So the derivative of the inside is epsilon I theta, like so. Then we have d theta. Alright, so then I'll L'Hopital, and notice that we have an e to the I theta, which will cancel out right here. And now we can clearly see what would happen if our epsilon goes to 0. this part right here, that's just going to vanish up to 0. So let's erase this right here. So in the end, integral over gamma 2 over f of z dz, that's going to be the integral from pi to 0 of 1 over this part right here, epsilon e to the I theta. That's going to vanish up to 0 in the limit, leaving us with, well, we have a double negative right here. So we have 8 times pi over 2, that's exactly 4 pi. So we have 4 pi down here. And then, well, all our thetas are gone. That's quite nice. We still have our d theta. And if we bring this out to the outside, we have 1 over 4 pi. And notice that switch these bounds are. That's looking kind of annoying. So we have 0 to pi, but now we're introducing a negative out here. So we have a minus out here. Integral from 0 to pi of d theta. And well, this thing right here, that's, since we're starting from 0, it's just going to evaluate to this upper bound right here. So now we have minus 1 over 4 pi times pi. These pi's are going to cancel each other out, leaving us with a minus a quarter. So what did we figure out right here? This statement isn't quite true because we actually need a limit out here. Limit as epsilon approaches 0 on the integral. But overall, we just found that if we take the limit as epsilon approaches 0 on the integral over gamma 2 of f of z dz, that's going to give us minus 1/4. And I guess I should just do the same for these two integrals as well. If we take the limit as our epsilon approaches 0 on this bottom line right here of working out, these are just going to disappear. It really doesn't matter what happens to them, they're just going to disappear off. And as for our contour integral over c, even as epsilon gets really small, we're still not going to have poles inside of our contour, so it's just going to stay as it is. Okay, so this integral over gamma 2, we found that it contributes a minus 1/4 term to our final result. Okay, now let's look at the integral over gamma 4. This is going to be quite similar. So I'm just going to go through this one quickly because it's going to be basically the same thing as the integral over gamma 2, just with a sign change. So integral over gamma 4. My marker's about to die. Maybe I should start using a new marker instead. I don't have another black marker. But I do have this blue marker right here, so let's just use this one. So integral over gamma 4 of f of z dz, that's exactly the integral over gamma 4 of e to the I z over pi squared minus 4z squared dz. Let's do our parametrization. So we're going to let z be equal to, now instead of minus pi over 2, we're going to be at pi over 2. And to form a circle around that, we're going to add epsilon e to the I theta. So that means that our dz is equal to derivative of this thing, which is I epsilon e to the I theta d theta. And of course our theta also goes from pi to 0. So theta goes from pi to 0 like so. So now if we plug everything in right here, this is going to give us the integral from pi to 0. E to the I, z is this thing right here, so pi over 2 plus epsilon e to the I theta over pi squared minus 4 pi over 2 plus epsilon e to the I theta squared, and then dz becomes I times epsilon e to the I theta d theta. Okay, and now same deal as before. This part right here in the limit, that's going to disappear off. This is going to leave us with an I right here. So we have an I, and I times I, that's exactly minus 1. So we have minus 1 right here, and minus 1, we can use that to switch the bounds of this integral, which is quite nice. So now we're going from 0 to pi. Okay, now we can get rid of that. Now this e to the I theta, that's just going to stay as it is, but now we're just going to move this epsilon up here and take a look at this part right here. If we take the limit as our epsilon approaches 0, again you can check for yourself, you're going to get a 0 divided by 0 situation. So we're just going to dd epsilon on the top and the bottom, just using some L'Hopital. And what we should get is the integral from 0 to pi. I'm going to write this first, so e to the I epsilon. Derivative of the top, that's 1, over derivative of the bottom, that's going to be minus 8 pi over 2 plus epsilon e to the I theta. So that's the derivative of the outside, just bring this 2 down, and then derivative of the inside again is e to the I theta. Then we still have our d theta. Notice that this and that will cancel each other out. And what are we left with right here? We're left with the limit as our epsilon approaches 0 on the integral over gamma 4 That's equal to, well, if this goes to 0, that's just going to disappear off, and we're left with minus 4 pi on the denominator right here. So we have the integral from 0 to pi of 1 over minus 4 pi d theta. Let's chuck that onto the outside. So this is equal to now minus 1 over 4 pi. This integral is just going to evaluate to pi, leaving us with minus a quarter. So in fact, we do get the exact same result as the integral over gamma 2. So it's just going to contribute another minus 1/4 to this. Okay, and as for the integral over big gamma, I'm not going to calculate it in this video because this video is dragging on for way too long now. But essentially what you would use for this integral is Jordan's lemma, because we're on an arc of a radius that's going off to infinity. Link to the proof of Jordan's lemma will be up here or in the description. But for now, this integral, that's just going to vanish off to 0 in the limit. Alright, so what are we left with right here? We're left with this expression right here. It looks a little bit messy, but essentially what we have is that 0 is equal to, I'm going to write these first right here. So 0 is equal to minus 1/2, because a quarter minus a quarter is minus a half. Plus, I'm going to factor out a 2 right here. So plus a 2. Then we have the integral. I'm going to write this integral first. So the integral from 0 to pi over 2 of cosine of x over pi squared minus 4x squared dx. And then we're going to add this with the integral from pi over 2 to r of cosine of x over pi squared minus 4x squared dx. So those are our two integrals, and we should probably take the limit as our r approaches infinity as well. And if we do, this is going to turn into infinity. This is going to turn into infinity. And well, we have the same functions right here, we just have different kind of intervals. And whenever you have that, well, just to add the two intervals together, so we're going to have 0 is equal to minus 1/2 plus 2 times the integral from 0 to infinity of cosine of x over pi squared minus 4x squared dx. And well, what can we do from here? We can move the 1/2 onto the other side, which means that we have half out here being equal to 2 times the integral from 0 to infinity. And to isolate this integral, we can divide both sides by 2, which means overall that the integral from 0 to infinity of this function right here is equal to a quarter. But the thing is, this integral isn't quite the integral that we started off with, because we started off with the integral from minus infinity to infinity of cosine of x, all divided by pi squared minus 4x squared dx. And well, notice that this integrand right here, that's actually an even integrand, because if you plug minus x into here, for example, x squared of a negative is just the x itself, and if you plug negative x into here, well, cosine is an even function, so it's going to give you the same value. So in fact, whenever you have an even function and you're integrating over symmetric bounds right here, so say from minus infinity to infinity, it's really the same thing as integrating from 0 to infinity and just doubling the result, because well, you're going to be finding this area right here, but you want the whole entire area, so you just multiply it by 2. So in fact, this integral, how it's related to this integral, it's just off by a factor of 2. So this integral is really twice the integral from 0 to infinity of cosine of x over pi squared minus 4x squared dx. And well, we can go back a couple steps and take a look at what I wrote before. But in order to get this integral out here, just multiply both sides by 2. So this is going to be a half right here. And so there you go, we have the answer of a half we're looking for, because these two integrals are the same thing. So overall, what's the final result? The integral from minus infinity to infinity of cosine of x over pi squared minus 4x squared is exactly equal to 1/2. So that's the final result for today's video. We solved it using complex analysis. That was quite a long video. If you made it through to the very end, if you watched the whole thing, then thank you very much. I greatly appreciate that. But yeah, hope you guys enjoyed, and I'll see everybody next time.